Welcome to the science classroom. As an instructor, your primary professional obligation is to maintain what we call a sanctuary of discovery. This means taking proactive steps to prevent foreseeable harm before an experiment even begins. This obligation is rooted in a legal concept known as the duty of care. If an emergency occurs, this framework determines your liability, meaning you are legally responsible for the safety of everyone in the room. Under TEA Texas safety standards, adequate space is a legal requirement. An elementary science classroom must provide a minimum of 41 net square feet per student. For the overall occupancy limit, you must maintain a strict ratio of 1 teacher to 24 students. Verifying these physical space and capacity requirements is step 1. You must secure this baseline before any scientific instruction can legally begin. Once the physical space is verified, you need to establish a culture of continuous safety. This requires a dedicated first-week safety plan, rather than a single isolated lecture. The first step in that plan is straightforward. You need both the students and their parents to sign a science safety contract on the very first day of class. This document functions as a legal shield for you, proving that rules were clearly communicated, while also serving as a pedagogical foundation that sets the behavior expectations for the student. Next, you transition to spatial awareness. Have the students create a safety map of the room. They will draw a floor plan on grid paper, checking off the locations of the eye wash station, fire blanket, extinguisher, and exits. By physically walking through the room to map these tools, students build muscle memory. If a crisis happens, they know exactly where to go, preventing panic and disorientation. Combining these spatial mapping exercises with signed safety contracts ensures everyone knows the protocol. This cuts down emergency response times and actively secures your baseline duty of care. Let's look at how this preparation pays off in a simulated emergency. A student accidentally knocks over a beaker of acid, and the chemical splashes directly up into their face. In this exact moment, hesitating is legally defined as nonfeasance, a failure to act. Freezing up and failing to direct the student to the eye wash station is a direct breach of your duty of care. You must step in immediately. The student will be temporarily blinded and in pain, so you need to physically guide them to the eye wash station and turn the water on. Once their face is in the water stream, you have to use firm hand placement to manually hold the student's eyelids open. This requires applying physical force, because the body's natural biological reflex is to squeeze injured eyes tightly shut. Overcoming that reflex is medically necessary to clear the chemical. This timer illustrates the safety standard's strict, non-negotiable time requirement. You must keep the eyes flushed in that water stream for 15 full minutes. Executing this 15-minute hold is physically uncomfortable for both of you, but completing it clears the chemical and specifically shields you, the instructor, from nonfeasance liability. Now let's address an escalating complication. The spilled chemical has reacted with the bench surface, igniting a secondary fire. You need to transition immediately to the fire blanket. Step 1 is safely pulling it down from its designated wall mount. Before approaching the flame, wrap the top edge of the heavy fabric over your hands. This grip shields your own skin from the extreme heat as you move in. You must lay the blanket down using a smooth, controlled smothering motion. If you panic and wildly throw the blanket at the bench, you commit misfeasance, an improper act that can fan the flames and increase your liability. If the blanket fails to smother the fire and the flames begin to spread beyond the immediate area, you have crossed the protocol threshold. You must abandon the blanket and retrieve the fire extinguisher. This diagram illustrates the pass method, which dictates the correct sequence for operating the extinguisher. You pull the pin, aim the nozzle at the base of the fire, squeeze the handle, and sweep from side to side until the fire is out. By mastering the exact physical techniques for the fire blanket and the extinguisher, you ensure a localized bench accident is quickly contained before escalating into a facility-wide disaster. With the student flushed and the fire fully extinguished, the emergency simulation is successfully resolved. Navigating an event like this proves why preparation matters. Integrating signed contracts, spatial mapping, and precise physical emergency responses creates an environment that is both safe and legally compliant.
Hey everyone, and welcome. I'm an instructor with Project Pace, and today we're going to tackle one of the most important things you'll do in your courses, submitting assignments in Canvas. My goal here is to make sure you can do this without any stress, so you can really focus on doing your best work. So, what are we getting into today? Here's our game plan. We're going to start with how to actually begin your submission, then we'll dive into all the different ways you can turn in your work. After that, we'll cover the big one, how to know for sure that it's turned in, and finally, we'll look at how to find your feedback. Sound good? Let's jump in.
All right, first things first. Before you can submit anything, you have to get the process started. It all begins with just a couple of simple clicks inside your course. Let's break down exactly what that looks like.
Okay, so the first thing you're going to do is navigate to your course and click to open up the assignment itself. Once you're on that page, look for a big button, usually hanging out in the top right corner, that says Submit Assignment. That button right there, that's your starting line.
But what happens if you get to the assignment page and poof, that button just isn't there? The first thing to know is don't panic. This happens sometimes, and there's almost always a perfectly logical reason for it.
See, if that button is missing, it's usually on purpose. For instance, maybe it's not an online submission at all. It could be an in-class presentation. Or the due date might have passed and the assignment is closed. If it's a group project, maybe one of your teammates already submitted for everyone. And sometimes it's just an ungraded task that doesn't need a formal submission.
Okay, so you've found the button, you've clicked it, and now you're in the submission area. This is where the magic happens. Let's explore the different ways your instructor might ask you to hand in your work. Now, here's a key thing to remember. You're not going to see every single one of these options for every assignment. Your instructor gets to pick and choose the best submission type for the task at hand, so you'll only see what they've made available. Let's start with the most common one you're going to see, the file upload. This is your classic option. It's perfect for turning in things like Word docs, PDFs, spreadsheets, images, pretty much any file you have saved on your computer. Using it is super simple. You just click Choose File or Browse and find the file on your computer. And hey, if you need to upload more than one file, no problem. Just look for the Add Another File link. A quick pro tip though, your instructor can limit which file types are allowed, so make sure you're uploading the right kind, like a PDF if that's what they asked for. Next up, we've got the text entry option. Instead of a file, you'll just see a text box, what Canvas calls the Rich Content Editor. This is great for shorter assignments, where you can just type your response right in, or even copy and paste it from somewhere else. No separate file needed.
So, what if your work isn't a file at all, but a website? Well, for things like a blog post you wrote, or maybe an online portfolio, you'll use the website URL option. You literally just copy the link to your work and paste it right into the box. Easy as that.
And for all you creative types making multimedia projects, there's the Media tab. This thing is really cool. It lets you record audio or video right there in Canvas using your computer's mic and camera. Or if you've already made your video, you can just upload the file directly. Okay, everybody lean in because this one is so important. You'll probably see a comments box on the submission page. That box is only for leaving a quick note for your instructor, like, hey, I had a question about part 2. It is absolutely not the place to paste your actual assignment. Always, always use the correct submission area. And this brings us to the final, most crucial step of all. It doesn't matter if you uploaded a file, typed in a response, or recorded a video. Nothing is officially turned in until you click that big final Submit Assignment button at the bottom. Seriously, don't forget this step.
So, you clicked Submit. You take a deep breath. But how do you really know it went through? Well, the good news is Canvas gives you instant confirmation, so you're not left wondering. Let me show you what to look for.
The second you hit Submit, just glance over to the sidebar on the right. You should see a wonderful confirmation message with the exact time and date you submitted it. If you happen to be late, it'll say so in bright red text. You'll also see a submission details link you can click for even more info. That's your proof it's turned in.
All right, we're on the home stretch. After you've submitted your work and your instructor has greeted it, the journey's not quite over. The final piece of the puzzle is going back to see your grade and all that valuable feedback.
When you go to your submission details, the View Feedback button is going to be your best friend. Clicking this will actually let you see your instructor's notes and comments marked directly on top of your original file. Now, if you submitted a weird file type that doesn't support that, you'll see a Preview button instead, which just lets you see the file. The submission details page has a few other handy tools too. You can download the exact file you submitted, which is great for your records. If your instructor used a rubric, you can click Show Rubric to see exactly how you were scored. And hey, if your instructor allows it, and it's before the due date, you might even see a Resubmit Assignment button. And just like that, you've got this. You now know everything you need to submit any kind of assignment in Canvas with total confidence. The technology is no longer a hurdle. So the only question left is, what amazing thing are you going to create and turn in next? I can't wait to see it. All right, let's dive in. If you're getting ready to teach science here in Texas, you already know that competencies 001 and 003 are, well, pretty much the foundation of everything. So today we're going to crack the code on these and turn them from just a list of rules into a real blueprint for building an amazing classroom, a sanctuary for scientific discovery. Let's get to it. First things first, let's get this core idea locked in. This quote, it really gets to the absolute heart of competency 001. A safe classroom isn't about putting up walls to limit what kids can do. No way. It's about creating a protected space where they feel secure enough to have those aha moments, to really explore without fear. It's the launchpad for everything else we're going to do. So here's our roadmap for today. First, we'll talk about the 2 hats every science teacher wears. Then we're going to forge our safety shield. That's all about competency 001. After that, we'll focus the precision lens on the tools and the data. Then we'll cover how to share what we find, and finally we'll connect it all to the big picture with science and the world, and that's where competency 003 really comes in.
Okay, first up, the teacher's 2 hats. This is all about getting a handle on your dual identity in the science classroom. And trust me, it's way more than just being the person who gives the lectures. It's about playing 2 roles that are totally distinct, but both are absolutely critical. So just imagine you're wearing 2 different hats all day long. With one hat on, you're the lead investigator. You're the one sparking that curiosity, you're modeling how to ask awesome questions, how to really think like a scientist. But at the exact same time, you're wearing your other hat, the chief safety officer. You're the guardian of that space, physically, legally, ethically. You really can't be one without the other. They're 2 sides of the very same coin. So now that we're clear on those 2 roles, let's really zero in on that Chief Safety Officer hat. This whole section is about forging that safety shield. We're talking about building the protective walls of our little Discovery sanctuary. And this gets right to the very core of competency 001. At the center of all classroom safety is this really important legal concept, duty of care. And as you can see, this isn't just a good idea or a best practice. It's your legal and professional obligation. It means you are responsible for anticipating and then preventing any harm that you could reasonably see coming. This is the why behind every single rule we're about to talk about.
So how does duty of care look in action? It looks like knowing your emergency protocols cold. I mean, these are the absolute non-negotiables. Goggles, they're on anytime there's heat, chemicals, or even tiny things flying around. You gotta know exactly where that eye wash station is. And remember, a splash isn't a quick rinse. We're talking a full 15 minutes of flushing. And of course, you have to know where the fire blanket and extinguisher are and be able to grab them in a heartbeat.
And speaking of fire extinguishers, here's how you use one. The pass method is just brilliant because it's so easy to remember, even when you're stressed. You pull the pin. You aim low, at the base of the fire, not up at the flames. You squeeze the handle, and you sweep from side to side. Just run through that in your head a few times until it's second nature.
Now for chemicals. Any chemical you use, I'm talking everything from basic vinegar to something more complex, comes with a document called a Safety Data Sheet, or an SDS. Think of this as the complete encyclopedia for that chemical. It tells you absolutely everything you need to know about its risks, how to handle it, and how to get rid of it safely. And yes, you are required to have one of these handy for every chemical you've got.
Now, don't worry, you don't need to memorize all 16 sections, but these 3, you've got to know them. Section 4 is your emergency plan, what to do if something goes wrong. Section 7 tells you how to store it correctly, and Section 13 is super important. That's how you dispose of it. And please, burn that rule at the bottom into your brain. Assume nothing goes down the sink. Always check the STS first. You know, your duty of care goes beyond just the people in your room. It also includes the ethical treatment of any organisms you have, whether they're living or preserved. That means keeping their habitats clean and healthy, and, this is a big one, Never, ever releasing a non-native species from your classroom out into the local environment. When you do this right, you're not just teaching science, you're modeling what it means to be a good steward of our world.
Okay, so our safety shield is forged, our sanctuary is protected. Now it's time to shift from the environment itself to the actual work we're going to do inside it. This is all about using the right tools and, speaking the language of science, which is another key piece of Competency 001. Choosing the right tool isn't just about what works for the experiment. It's about what's right for the student's age and stage. You can really see the progression here, right? We start super simple and concrete in kindergarten and first grade. Think hand lenses and measuring things with paper clips. But by the time they're in fourth and fifth grade, they're ready to graduate to more precise instruments like triple beam balances and microscopes. Now, let's quickly clear up two words that get mixed up all the time: accuracy and precision. Think of it like throwing darts. Accuracy is how close you get to the bullseye. Precision is how tightly you can group your darts together, even if that group isn't on the bullseye. So you can be really precise without being accurate. Of course, in science, the goal is to be both. So what makes us miss the mark? Well, it usually boils down to two main culprits. First, there's systematic error. That's a problem with the tool itself, like a scale that wasn't zeroed out. It's going to make all your measurements consistently off. Then there's human error, which is a mistake in how you use the tool, like reading a graduated cylinder from an angle instead of at eye level. Knowing these two helps you and your students figure out what went wrong in an experiment. Look, getting the data is just the beginning. The next step, which is just as important, is to organize it and present it in a way that tells a clear, honest story. This is how we turn a bunch of numbers into actual knowledge. And step one is always organization. A nice, clean data table like this one is your best friend. It takes all that messy data you scribbled in your notebook and puts it into a structure that makes sense. You can't make a graph, you can't draw a conclusion until you've got your data organized in a table. It's the foundation. Okay, once your data is organized, you can make it visual. Now, if your goal is to compare different groups, like the final height of plant A versus plant B, a bar graph is perfect. It gives you this immediate, really powerful visual. You can see the difference between the categories in a split second. The comparison just pops. But what if you want to show how something changed over time? Well, that's where a line graph is the star of the show. So if we took our plant data, we could connect the dots for plant A's height on day 1, day 3, and day 5. Suddenly, you're not just comparing the end result, you're showing a trend, a pattern of how that growth happened over a continuous stretch of time. And for our last section, let's zoom all the way out. This is where Competency 003 really shines. It's all about making the connection between the labs you do in your room and the world outside the classroom walls. It's about showing students why this stuff actually matters. Because science isn't just a subject, right? It's a tool for living your life. It's what helps us make smart choices about our own health and nutrition. It's what guides these huge decisions we make as a society about our planet. I mean, just understanding the difference between solar power and coal, that comes directly from being scientifically literate. And this is so important. We have to show students that science is a human story. It's not some ancient book of facts that never changes. It's a living, breathing process of discovery that's always evolving. And it's a story that's been written by incredible people from every background imaginable. People like Katherine Johnson, who did the math to get us to the moon, or Mario Molina, who helped save the ozone layer. Sharing their stories shows every single one of your students that they can be a part of this adventure too. So, we end right back where we began. You're not just getting ready to teach a subject. You are preparing to build a sanctuary, a safe place for discovery. You've got the blueprint now with Competency 001 and 003. So the only question left is, how are you going to build yours? All right, let's jump right in. For your mission today, I want you to stop thinking like a teacher in training and start thinking like a biosystems engineer. We're going to tackle the life science part of the TESAS 904 exam by looking at the living world through a completely different lens. So, welcome to the briefing. Your main goal here is to get a handle on the core principles of living systems. You know, how they're built, how they're coded, and how they all connect. This is your official debrief for competencies 011 through 014. Let's get to it. Okay, first things first, we've got to look at the basic hardware.
This is all about competency 011, understanding the structure and function of living things. I mean, you can't work on a machine until you know what makes it tick, right?
So, let's run some basic diagnostics. What's the real difference between a biological machine and, I don't know, a toaster? Well, it all comes down to a few key specs. Living systems are made of cells, they need fuel, they grow, they make copies of themselves, and they react to what's going on around them. A non-living thing? It does none of that. This idea right here is the absolute foundation of all life science.
Now, this is where it gets really cool. How are these things actually put together? It's all about levels of organization. You start with the tiniest building blocks, the cells. You group those together, you get tissues. Tissues work together to form organs. Organs get networked into organ systems, and all of those systems together create the complete organism. It's an incredible example of modular design.
And here's that integration in action. Just look at the human body. You've got all these amazing subsystems working together. The skeleton, that's your chassis, your framework. The muscles, that's your engine, providing movement. The circulatory system is the fuel line, and the whole thing is run by the nervous system. That's the central computer. And the most important part? Nothing works alone. It's all connected.
Okay, so we've covered the hardware. Now it's time to dig into the software that makes it all run. This is competency 012, all about heredity and reproduction, or as we're calling it, the coding of life.
And at the heart of all that biological software is DNA. Honestly, you can just think of it as the ultimate instruction manual. This one molecule, it contains every single line of code needed to build and run an entire organism. It's mind-blowing, really. Everything from your eye color to your heartbeat is written in this code. If you want to understand the machine, you have to understand the code.
So, how does this amazing code get passed on to the next model? Well, there are basically two main methods. You've got asexual reproduction, which is kind of like cloning. You get a perfect, identical copy from just one parent. Then you've got sexual reproduction, which is more like a remix. It combines the code from two parents to create something totally new and unique.
And what's really cool is that we can actually predict how that genetic remixing is going to turn out. We use a tool called a Punnett square. It shows us the probability of different traits. So see the big G? That's a dominant gene. Think of it as the loud one. If it's there, you're going to see its trait. The little g is recessive. It's quieter. You only see its trait if it's paired with another recessive gene. This simple little chart is a powerful forecasting tool. Now, this is a really important distinction you have to make. Think of it like factory settings versus user customizations. Inherited traits, like your hair color, are hard-coded right into the DNA from the start. But learned characteristics, like speaking a language or riding a bike, those are like software updates you get from experience. One gets passed down through generations, the other doesn't. Okay, on to our next section. These biological machines, they aren't static. They get upgrades over time. And that brings us to competency 013, adaptation and evolution. You can think of this as the ongoing, long-term research and development department for life itself. So, how does this R&D work? Well, it's basically one giant, continuous field test. The environment itself is the ultimate quality control inspector. This process, natural selection, is what decides which designs work and which ones don't. Any trait that helps an organism survive and reproduce gets selected and passed on, constantly improving the design over millions and millions of years. And these upgrades come in two main flavors. You've got your physical adaptations, those are hardware changes. Think of a bird's beak changing shape over generations to be perfect for cracking a specific kind of seed. Then you've got behavioral adaptations. Those are software updates. Think of birds changing their migration patterns because the seasons are shifting. Both are all about survival. All right, for our final section, we're going to pull the camera way, way back because no machine, no organism operates in a bubble. This is competency 014. And it's all about how these individual units plug into the huge, complex network we call an ecosystem. In this giant network, everybody's got a job to do. You've got the producers, like plants. They're the power plants, making energy from the sun. Then you have the consumers, who get their energy by eating other things. And finally, you have the decomposers. They're the cleanup crew, breaking down dead stuff and recycling all the raw materials back into the system. Now, take a look at how energy actually moves through this network. It's not very efficient. That's the big takeaway here. As you go up the food chain, only about 10% of the energy from one level actually makes it to the next. This is why you have a pyramid shape. It shows you just how much the entire system depends on that massive energy base created by the producers at the very bottom. But
What happens when you throw a wrench in the works? System disruptors. Things like climate change or human activity can cause major instability. It's like pulling a thread on a sweater. You can break links in the food web, push the system beyond its limits, and trigger a chain reaction that threatens the whole network. And with that, your briefing on Life Science Competencies 011 through 014 is officially done. We've gone over the hardware, the software, the R&D process, and the integrated network. Consider the final quality assurance check complete. So now, your real mission begins. Everything we just covered, that's your new toolkit. So I want you to think about this question. How are you, as the lead engineer in your own classroom, going to translate all of this? How will you empower the next generation to understand and, more importantly, protect these amazing biological networks?
All right, future educators, welcome. This is your specialized explainer for the Earth and Space Science domain of the Texas 904. If that's the test you're prepping for, you're in exactly the right spot. So let's just jump right in.
Okay, let's start with the most important number you're going to see, 22%. That's how much of your final score comes from these Earth and Space Science competencies. It's a huge piece of the pie, so you can see why mastering this section is absolutely crucial for your success.
So how do we tackle that 22%? We're going to change our mindset. For this session, you're not just a future teacher studying for a test. Oh no, you are a planetary architect. We're going to look at Earth not as a boring list of facts to memorize, but as a series of beautifully engineered, interconnected systems that you need to know inside and out.
And here's our game plan, our blueprint, if you will. We're starting with the foundation, the crusto-build. Then we'll check our materials with the cyclic inventory, fire up the power grid with the energy regulator, and then zoom out to see the neighborhood in the celestial array. And of course, we'll finish up with a final integrity check, just to make sure everything is ready to go.
All right, let's get to it. Our first theme, the crustal build. This is all about competency 015, which covers the basic architecture of our planet. You know, its solid ground, the water that covers it, and the very air that surrounds it.
Now, check this out. What we've done here is translate that official Texas jargon into an architect's actual to-do list. See, you're not just learning about plate tectonics, you're analyzing tectonic build and demolition. You're not just studying the air, you're reviewing the specs for the atmospheric shield. It just makes these huge ideas feel so much more hands-on, doesn't it?
So, here's the main takeaway. The Earth's surface is in this constant state of push and pull, a cycle of construction and demolition. You have these massive tectonic forces building things up, like mountains, and at the exact same time, you have weathering and erosion trying to tear them all down. And then you throw in what we call system disruptors, both human and natural, that can change the entire blueprint in an instant.
Okay, so we've got the planet's structure down. Now let's talk about how it manages all its materials. This brings us to Theme 2, the cyclic inventory. This covers Competency 016, and it's all about how Earth's most essential resources are constantly being cycled and recycled.
Just think of this table as your master inventory sheet. I mean, any good planetary architect has to keep track of their key materials, right? You've got the rock cycle managing the solids, the water cycle for all the liquids, and then nutrient cycles for the really essential stuff, like carbon and nitrogen. It's all about flow, transformation, and reuse.
And this right here? This is one of the planet's oldest and, frankly, most amazing recycling programs, the rock cycle. And it's not a straight line. You can have an igneous rock that gets worn down into sand, which then gets squished into a sedimentary rock, which can then get cooked and squeezed into a metamorphic rock. It's a total remodeling process that never ever stops.
You know, this brings up a really critical question for any architect. What are the specs for these materials? It's not enough to just know that they cycle. You have to understand their specific properties and why they are so important to the planet's grand design.
And here are those specs. The specific properties of rocks, soil, water, and even the gases in our atmosphere. They determine what these materials can do. And for you as a future educator, being able to connect these properties to their real-world uses is absolutely key to making this science come alive for your students.
All right, so we've covered the structure and the materials. Now let's talk about the power grid. Theme 3 is the energy regulator, and this lines up with Competency 017. This is all about how our planet manages the constant flow of energy, which is what drives our weather and ultimately creates our climate. Welcome to the Planetary Control Room. Your meteorological dashboard is where you're watching the day-to-day stuff, like temperature and air pressure, but a good architect also has to understand the long-term system settings,
That's the system calibration, distinguishing weather from climate, and the crucial orientation specs, like the planet's tilt, that really run the whole show. And this comparison, this is so important. For the test and for your classroom later on, you have to be crystal clear on the difference between weather and climate. And the easiest way to think about it is right there on the screen. Weather is what you get. Climate is what you expect. It's the difference between the outfit you choose to wear today and the contents of your entire closet.
Okay, for a final theme, as the planetary architect, it's time to zoom out, way out. We've designed our planet, and now we need to see where it fits in its cosmic neighborhood. This is Theme 4, the Celestial Array, and it covers Competency 018, our planet's place in the whole universe.
This is the master schematic, the site plan for the whole development. It shows how our world interacts with everything around it. And the most important job for the architect here is to understand what we call orbital synchronization, that beautiful, predictable, gravitational dance between the Earth, the Moon, and the Sun.
You know, this gravitational dance is responsible for the most basic rhythms of our lives. This isn't just some abstract thing happening out in space. It's the powerful, predictable clockwork that gives us our days and nights, our seasons, the tides in our oceans, and even spectacular events like eclipses.
And this timeline perfectly shows us why we have seasons. It all comes down to one of Earth's key orientation specs, its 23.5-degree tilt on its axis. As we orbit the Sun, that tilt means different parts of the planet get more direct sunlight at different times of the year. It's a surprisingly simple idea that has enormous effects on all of us.
Well, we've gone through the entire blueprint. But you know, before any project is truly finished, a good architect always does one last structural integrity check. So this is it, your final punch list to review before exam day. Okay, here's the bottom line. If you can confidently walk someone through these 4 high-impact concepts, you are in fantastic shape for the exam. Make sure you can explain the WED process, the predictable patterns of the celestial clockwork, how pressure systems drive our weather, and that continuous rock cycle remodel.
And that's it. You have the framework. You have the planetary architect's blueprint to understand these massive, complex Earth and space systems. You know the structure, the inventory, the power grid, and the cosmic layout. You've got this. And that really just leaves us with one final thought. The real challenge, the real test, isn't just about passing this exam. It's about taking this blueprint and using it to architect curiosity and engagement and a real, genuine understanding for your future students. Good luck.
All right, let's get right into it. Welcome to our review for the Texas Science 904, Module 4. We're going to tackle the big physical science competencies you've absolutely got to master for the exam. We're breaking down matter, motion, and energy into a framework that just clicks. Okay, to really get this, I want you to adopt a certain mindset. For today, you are a systems mechanic. Now, this isn't just some catchy name, it's a whole new way of looking at things. It means you see the universe not as a bunch of random stuff happening, but as this beautifully complex machine, a system that follows predictable rules, and you're the one who gets how it all works. So, here's our game plan. First, we're going to solidify that systems mechanic mindset. Then we'll get our hands dirty and inspect the 3 core components of our system. The materials, which is all about matter, the mechanics, which covers force and motion, and the power, which is, you guessed it, energy. And to wrap it all up, we'll assemble your very own teacher tool. All right, first up, materials. You can't work on any system if you don't know what it's made of, right? This part is all about Competency 008, getting a real handle on the fundamental stuff of the universe, what it is, what its properties are, and how it can change. So the most basic property of matter is its state. Let's think about the molecules. In solids, they're packed together, shoulder to shoulder, not going anywhere. In liquids, they've got a little wiggle room. They can slide past each other. And gases, well, that's like recess. The molecules are just zipping around all over the place. The key thing you'll want to get across to your students is that it's all about the behavior of those molecules. Now, what happens when this stuff changes? This is a huge one you've got to nail down. A physical change is like changing an outfit. When ice melts, it's still H2O, it just looks different. But a chemical change? Whoa, that's a total identity switch. When iron rusts, it becomes a completely new substance, iron oxide. So the question you've always got to ask is, did the stuff fundamentally become something else? We can also sort matter by how it's put together. Think of it like Legos. Elements are your basic individual bricks,
all one type, like a pile of red bricks. Compounds are what you get when you snap different bricks together to build something totally new, like H2O. And mixtures? That's just tossing all your different bricks into the same bin. They're together, but they're not connected.
Okay, let's pause for a second. Time for a systems mechanic spotlight. See, some properties are just descriptive, but others are predictive. They let you figure out what's going to happen. And one of the most important ones you've got to master is density.
And the formula looks simple because the idea is simple. It's just a measure of how much stuff, that's the mass, is crammed into a certain amount of space, that's the volume. Once you get a handle on this little formula, you can predict whether something will sink or float. It's a classic for a reason and a concept you'll use all the time.
Okay, so we've got our materials, we know what the universe is made of, but how does it all move? That question brings us to our next section, mechanics. This is all about competency 007, mastering the relationship between force and motion. I mean, seriously, think about it. This is one of the first big questions a kid asks about science. As the systems mechanic in the room, you need a crisp, clear answer ready to go. And the cool thing is, the answer is actually incredibly elegant. And the answer, in 2 words, is unbalanced forces. That's it. Things want to keep doing what they're already doing. If you want to make a box move, your push has to be stronger than the force of friction pushing back. It's like a cosmic tug of war, and somebody has to win for there to be any change. This simple idea applies to everything from a seesaw to the movement of tectonic plates. And these pushes and pulls aren't just random chaos. Oh no, there are rules. There are a few, let's call them heavy hitters, in charge of how everything interacts. We're talking about the big ones: gravity, electricity, and magnetism. They're the ones writing the rulebook for motion across the entire universe. So, let's recap. We have our materials, the parts. We have the mechanics, the rules for movement. What's the one thing we're missing? The engine, the power source. This brings us to competencies 009 and 0110, which are all about energy, what it is, how it flows, and how it transforms. So let's pop open our energy toolkit. At its heart, energy really comes in 2 main flavors. You've got potential energy, which is stored up, waiting to happen energy, like a stretched rubber band. And you've got kinetic energy, which is happening right now energy, the energy of motion. And these 2 basic types can show up in all sorts of different forms. And here's the really cool part. Energy is a master of disguise. It's constantly changing forms. A hydroelectric plant is the perfect example. You start with the potential energy of all that water just sitting there behind a dam. Then, whoosh, it falls, transforming into kinetic energy. That moving water spins a turbine, which then transforms that energy into the electrical energy that powers our world. It's one amazing chain reaction. Heat energy is a big one, and it gets around in 3 predictable ways. There's conduction, which is just direct touch, like grabbing a hot pan handle. There's convection, which is heat moving through fluids like air or water. Think of hot air rising. And then there's radiation, which is heat traveling as waves through space. You don't have to touch the sun to feel its warmth, right? This all leads us to maybe the single most important rule in the entire systems mechanic handbook. We're calling it the law of the build, and it's simple. You cannot create energy from nothing, and you can't make it just disappear. You can only change its form. This, my friends, is the law of conservation of energy, and it's a non-negotiable rule of the universe. And once you know this law, you start to see it absolutely everywhere. Look at this. Photosynthesis. That's a plant taking light energy from the sun and transforming it into chemical energy, food. Then an animal eats that plant and the food web takes over, transforming that chemical energy into the kinetic energy for movement and thermal energy for warmth. The energy just keeps getting passed along in changing costumes, but it's never, ever lost. Okay, we've inspected the materials, we've figured out the mechanics, and we've understood the power source. Now for our final step, let's put it all together and assemble your official systems mechanic toolkit. So here it is. Your toolkit has 3 essential tools. Number 1, a deep knowledge of materials so you know what things are made of. Number 2, a solid mastery of mechanics so you know what makes things move. And number 3, a clear map of power so you understand how energy drives the whole show and is always conserved. Get these 3, and you've got the foundation of physical science down cold. And that brings us to the final, most important thought. This whole thing, it's not just about information to pass an exam.
It's about giving you a powerful toolkit you can use to build real, genuine understanding in your future students. So the real question isn't just about what you know, it's about what you're going to build with it. How will you use this toolkit to help your students see the truly elegant, interconnected system that governs our universe?
Hey there, and welcome. If you're getting ready for the Texas Science exam, you know it's about more than just facts and figures. It's really about a whole new way of thinking about teaching. Today, we're going to flip the script on your role in the classroom. You're not just a presenter, you're something way cooler, an architect of inquiry.
You know, for a long time, science was taught like that tower on the left, just a big, finished building of facts you had to memorize. But that's not what science is. The view on the right, that's the real deal. Science is this messy, exciting, ongoing construction project. We're always building, testing, and even knocking down walls to build something better. And honestly, that one little shift in perspective changes absolutely everything about how we should teach it.
So, okay, if science is a construction project, where do you fit in? Well, that makes you the architect. Your job isn't just to walk students through a finished museum. No way. Your job is to hand them the blueprint, the tools, and the support they need to start building their own understanding, brick by brick.
So, here's our game plan for this explainer. We'll start with your role as the architect. Then we'll get into your toolkit, the blueprint, which is really the nature of science itself, the lenses, these big unifying ideas that connect everything, and the scaffold, which are the teaching methods you use to support your students. And then, at the end, we'll see how it all comes together to create a true masterpiece.
All right, first things first. Every great project needs a blueprint. For us, that's Texas Competency 002, the nature of science. This is all about the how and why science works. It's the set of rules we follow to make sure that what we're building is actually strong, it makes sense, and it's based on solid evidence.
And the foundation. The very first thing you lay down is a testable question. Now, this is key. It's not just any old question. It's a question you can answer by actually doing something and collecting data. So a question like, which brand of paper towel soaks up the most water? Yep, that's testable. But which brand is the best? Not so much. That's an opinion. Helping your students learn to ask good, testable questions is job number one for the architect.
And you know, it's also important to realize that inquiry isn't just a one-size-fits-all thing. It's more like a ladder. Students often start with descriptive investigations. That's just pure observation. What do I see? What's happening? Then they can climb up a step to comparative investigations, where they start looking for what's the same and what's different. And finally, they can reach the top with experimental investigations. That's where they get to ask, okay, what happens if I change just one little thing? It's a fantastic way to build up their thinking skills.
And these are the non-negotiables. These are the building codes for science. Everything has to be based on evidence you can actually check. It has to be logical. And this one is so important. We have to teach kids that science is tentative. That doesn't mean it's wrong. It just means it's our best understanding for now, and it can always change when new evidence comes along. That's what keeps science honest and moving forward.
Okay, let's grab our next tool. These are the lenses. This connects to Texas Competency 004, which is all about the huge, unifying themes that you see again and again across all branches of science. Think of them like special glasses that let an architect see all the hidden patterns and connections that tie everything together, from a single cell to an entire galaxy.
Our first lens helps us see in terms of systems and models. A system is just a bunch of parts working together, right? Like the organs in your body or the planets orbiting the sun. And since these systems can get super complicated, we use models, things like a diagram of a plant cell or even a computer simulation, to make them simpler and easier to wrap our heads around.
The next lens is all about spotting patterns and cycles. You could almost say that science is the search for patterns. Once we see the repeating pattern of the seasons, or the predictable cycle of the moon, or the life cycle of a frog, we suddenly have this incredible power, the power to make predictions. It's how we bring order to what might otherwise seem like chaos.
And our final lens reveals this really cool dance between change and constancy. In every system you look at, there are forces trying to keep things stable and balanced. That's constancy, or equilibrium. But at the very same time, there are other forces pushing for change, like erosion or evolution. Understanding that push and pull is totally key to seeing how the natural world really works.
So, you've got your blueprint, you've got your lenses, but how do you actually help your students start building? Well, you need a scaffold. And that brings us to TEXES Competency 005, the nuts and bolts of how to teach science effectively. This is the structure you build around your students to keep them safe and supported as they climb.
And one of the best, most proven scaffolds out there is the 5E model. It's a simple, powerful cycle. First, you engage them, get them hooked with a cool question or a weird phenomenon. Then, you let them explore to get their hands dirty and mess around with it. Next comes the explain phase, where you help them connect what they found to the actual science concepts. After that, they elaborate, trying to apply what they learned to a new problem. And finally, you evaluate their understanding, not just at the end, but all the way through.
And that's the whole point, right? A model like the 5Es really hammers home this big shift in your job description. You're not the sage on the stage just giving out answers. You're the guide on the side. You are the architect, providing the support and the guidance, but they're the ones doing the heavy lifting and the actual building.
All right, let's bring it all home. We have the blueprint, we have the lenses, and we have the scaffold. How do these three things work together to create something truly special in your classroom?
This chart just lays it all out so perfectly. The blueprint, which is competency 002, is what you use to plan the whole investigation. The lenses, from competency 004, are what you use to help kids find those deep, meaningful connections. And the scaffold, from competency 005, is how you support them while they learn. See? They're not separate things at all. They're all part of one integrated system for building real knowledge.
And that's the real masterpiece. That's the end goal. When you fully embrace your role as the architect of inquiry, you're doing so much more than just teaching facts for a test. You are truly empowering your students to become confident, capable builders of their own knowledge for the rest of their lives. So, as you keep studying for your exam, and more importantly, as you get ready for your own classroom, I want to leave you with this question. You have the blueprint for inquiry, you have the lenses to see the world in a new way, and you have the scaffold to support the whole process. Now that you've got the tools, what incredible things are you going to help your students build?
All right, so if you're a future science teacher getting ready for that big Texas exam, let me ask you something. What if the secret to acing it wasn't about thinking like a teacher, but thinking more like an engineer? In this explainer, we're going to build the blueprint you need to master competency point 006, which is all about the principles of science assessment. So let's dive right in, because we are about to completely reframe how you think about testing. I want you to get this idea in your head. You're not just a builder of lessons. You are something more. You're a mastery engineer. See, this isn't just about constructing knowledge anymore. It's about making sure that what you build is solid, secure, and ready for any challenge that gets thrown at it. So what does a mastery engineer actually do? Well, you validate that learning is really happening. You reinforce the structure whenever you find a weak spot. And maybe most importantly, you maintain the conceptual integrity of the science you're teaching. It's a huge shift in thinking, right? You're moving from just delivering content to actually verifying that the structure is sound for every single student. Okay, so every great engineering project starts with a blueprint, a solid plan. For us, that's the inspection plan. This is all about laying the groundwork for success before you even teach the first lesson. It's about being intentional from the get-go. The number one principle here is something called backwards design. You've got to start with the end in mind. Before you plan a single activity, you need to know exactly what that finish line looks like. What does real mastery of a concept look like and feel like? Once you define that, then you can communicate those evaluation criteria clearly to your students. And that, right there, is a huge part of the Texas exam's descriptor 006.d. Let's keep this engineering metaphor going because it works so well. Think of formative assessments as stress tests. These are your quick, ongoing checks you do while you're still building the lesson, like an exit ticket or a simple thumbs up, thumbs down. You're just looking for weak points. Then you have summative assessments. Those are the final validation. That's the big inspection after the whole thing is built, like a unit test or final project. You absolutely need both to make sure the whole structure is sound. Assessment isn't some separate thing you tack on at the end. It's woven right into the fabric of your teaching. The 5E model is the perfect engineering scaffold for this. You're assessing from the very beginning, in the engage phase, just to see what students already know. And you keep assessing all the way through to the final evaluate phase. Each step has its own assessment purpose, which really shows that deep connection between instruction and assessment that descriptor 006.A is all about. All right, we've got our plan. Now we need the right tools. An engineer is only as good as their instruments, right? It's the same for us. We need authentic tools that can measure the quality of student learning, not just whether they can remember a few facts. And this is where we really move beyond those simple multiple-choice tests. We're talking about evaluating the capstone project, that big, culminating piece of work that shows what a student actually knows and what they can do. This could be anything: a detailed lab journal, a comprehensive portfolio. These kinds of products give us a much richer, more authentic picture of a student's understanding.
So how do we grade these bigger, more complex projects? Well, we've got two main tools in our belt. A checklist is pretty simple. It just asks, is it done? The measurement is totally binary, yes or no. But a rubric is so much more powerful. A rubric asks, how well is it done? It gives you a multi-dimensional measurement of quality. That's our precision instrument.
Let's dig a little deeper into engineering that rubric. You've basically got two main types. An analytic rubric breaks the project down and lets you evaluate each piece separately. This is amazing for giving really specific, actionable feedback. Then you've got the holistic rubric, which gives you one overall score for the whole thing. It's definitely faster for grading, but the feedback isn't quite as detailed. Choosing the right one just depends on what your goal is for that specific inspection.
And here's a really crucial point. Performance-based testing is all about active validation. It's got two parts that you can't mix up. The task is the performance. It's what the student actually does. The rubric is the evaluation tool. It's how you, the engineer, measure the quality of that performance. They have to work together to give you that complete picture.
Okay, so the inspection is done and we've got our results. But a mastery engineer's job is far from over. In fact, this next part is maybe the most important: reinforcing the structure. This is where we use the data we've collected to actively go in and strengthen student understanding. This is where the real learning kicks in.
Think of this as your structural repair cycle. Step 1, gather the data from your assessments. Step 2, identify the gaps. Where are the common cracks in their understanding? And step 3, provide just-in-time support. Now, this isn't about reteaching the entire unit to the whole class. It's about targeted, almost surgical reinforcement delivered exactly when and where it's needed most. And here is one of the most powerful tools you have, and it's student self-assessment. This is where you actually empower your students to become their own quality inspectors. By using things like reflection journals or learning logs, students start to use metacognition. They're literally thinking about their own thinking, and that builds an incredible sense of ownership over their own learning.
And finally, you have to communicate the results. Think about your feedback as an official inspection report. It can't just be a number or letter grade. To actually work, it has to be specific, telling students exactly where the problem is. It's got to be actionable, telling them what to do next, and it has to be transparent. That's how you close the learning loop and make sure the structure is even stronger for the next build.
So, we've talked about the plan, the tools, and the repairs. But there is one single engineering mandate, one core principle that holds this entire thing together. It's the non-negotiable foundation for absolutely everything we've talked about.
This is the golden thread of alignment. It's so simple, but it is so critical. The verb in your state standard, your text, that's your blueprint. So if that blueprint verb says students need to analyze, then your assessment must require them to analyze. A simple recall question just won't cut it. The cognitive level of the standard and the assessment have to match perfectly. If they don't, you're not actually measuring what you're supposed to be measuring. It's as simple as that.
So as you get ready to step into your own classroom, the real question isn't just what am I going to teach? The real question is, how am I going to engineer success? The TESES exam, that's just your first checkpoint. The real work, the important work, begins with your students. So, as a mastery engineer, what will be the first blueprint you design for their success?
Hey, Project Pace learners, and welcome. So, in this quick guide, we're going to walk through a tool that's, well, it's absolutely essential for your success here. I'm talking about the Canvas inbox. You know, as a future educator, clear and professional communication is a skill you'll be using every single day. And guess what? We're going to start practicing it right here, right now, in Canvas.
You know the feeling, right? We've all been there. You're deep into a module, you're working through the material, and then bam, you hit a snag. Or maybe a question just pops into your head that you have to get answered before you can move on. So what do? What's the best way to get that help, quickly and effectively?
Well, the answer is the Canvas inbox. This is your go-to spot for communicating directly with your instructors. And I want you to think of it as more than just some email system, okay? It's really a dedicated professional space for communication, built right into our learning environment. Okay, so where's this thing? Honestly, it could not be easier to find. Just look over to the main navigation menu, that dark bar that runs down the far left side of your screen. You're going to see an icon that says Inbox. Yep, that's where you're headed. All right, let's dive right in. I'm going to walk you through the practical steps of sending your very first message. I promise, it's super straightforward, and once you've done it just one time, it'll totally be second nature. Okay, first things first, you're going to click the Compose icon. It usually looks like a little pencil and paper. Now, this next step is really important. Make sure you select the correct course from the drop-down. This helps your instructor immediately know the context for your question, which is a huge help. After that, in the To field, just start typing your instructor's name and Canvas will find them for you. Easy. Then write a clear subject line, compose your message, and when you're ready, just hit send. And this brings us to a really, really important point about your mindset. Remember, you're a future educator. Every single professional interaction you have, starting now, is valuable practice. Seriously. The way you communicate here, it's a preview of how you'll communicate in your career. So just remember, this isn't a text to a friend. It's a professional message. So what does that professional tone even look like? It's actually pretty simple. Use a subject line that gets right to the point. Something like, question on the week 3 reflection. Always start with a polite greeting. State your question as clearly as you possibly can. And please always sign off with your name. Trust me, these small habits, they make a huge, huge difference. But what if typing it out just isn't cutting it, Sometimes a problem is just easier to explain out loud. Maybe you're hitting a weird technical issue, or a concept is just so complex that it would be way, way easier to just talk it through. So what do you do then? Well, Canva has this awesome feature for exactly this situation. Right inside the message box, you'll see these little icons to record a short audio or even a video clip. This is perfect for talking your instructor through a complicated question, or even better, showing them a technical issue you're seeing on your screen. It is such a helpful tool for getting your point across with, perfect clarity. Awesome. So, you've sent your message like a total pro. Now let's flip to the other side of the conversation. What happens next? Let's talk about receiving and reading the replies from your instructors. So, you've asked your question, and now you're waiting for that guidance. But listen, you don't have to sit there hitting refresh every 5 minutes. Canvas has a super simple way of letting you know when a reply is waiting for you. It's so simple. Just keep an eye on that inbox icon in the main navigation menu. When you see a little blue dot pop up next to it, sometimes with a number, that's it. That's your signal. You've got a new message waiting for you. And once you see that little dot, all you have to do is click on the inbox, find the message thread, it'll be highlighted to show it's unread, and just click on it. That'll open it right up so you can read your instructor's reply. It really is as simple as that. Okay, so let's bring this all together. Mastering this one simple tool, it's about so much more than just sending and receiving messages. It's really about you taking an active professional role in your own learning journey. Here's the takeaway, the really crucial point. The Canvas inbox is your direct line to support in this program. I mean it. It's how you ask for help, how you get clarification, and how you start to build a strong professional relationship with your instructors. When you use it well, you're empowering yourself to get the support you need exactly when you need it. So I'll leave you with this final thought to chew on. The habits you're building right now, here in Project Pace, the clarity in your questions, the professionalism in your tone, these are the exact same skills you're going to be modeling for your own students one day. So think about it. How can mastering this one simple tool today help shape the amazing educator you're going to become tomorrow? Hey everyone, and welcome to Project Pace. We're going to jump right in and talk about a tool that is honestly going to be one of your best friends here. I'm talking, of course, about the Canvas inbox. I mean, we've all been there, right? You're cruising through an assignment, everything's making sense, and then, boom, you hit a wall. Or maybe a question pops into your head and you just can't move on until you get it answered. So what's the move? Well, your best move is always the Canvas inbox. This is your direct line, your go-to spot for talking with your instructors. It's basically a professional, dedicated email system built right into Canvas just for us. Okay, so now that you know what it is, let's talk about where it is. It's your professional lifeline, so you gotta know how to find it, right? And honestly, they couldn't have made it any easier. See that main navigation menu on the far left side of your screen? That dark vertical bar? Just look for the icon labeled Inbox. That's it. That's your spot. All right, You found it. Now let's actually send a message. We'll do a quick step-by-step, and I promise after you do this once, you won't even have to think about it again. Okay, so first you're going to click that compose icon. Now this next part is super important. Make sure you select the right course from that little drop-down menu. From there, just start typing your instructor's name in the to field. It'll pop right up. Write your message, give it a quick proofread, and hit that send button. So sending the message is the easy part, but how you write that message, well, that's where we get into something really important. Remember, you're all on the path to becoming educators. Every single email, every message you send from here on out, it's practice for your professional career. So what does that look like in practice? It's actually really simple stuff. Give it a clear, direct subject line so your instructor knows what it's about. Start with a simple, polite greeting. Get straight to your question. Be as clear as you can. And always, always sign off with your name. These little things, they make a world of difference. Just think about it this way. How you communicate here is basically a sneak peek of the professional you're becoming. So just remember, this isn't like a text to a friend, you know? It's a professional message, and it's a reflection of you as a future educator. But hey, what happens when you've got a question that's just really hard to put into words? Or maybe you're running into a technical glitch and you want to show what's happening. Well, Canvas has this amazing feature where you can actually record a quick audio or video message right there in the inbox. It's perfect for those tricky situations where typing just doesn't cut. Okay, awesome. You've sent a clear, professional message. You're a pro at this already. Now, let's flip the script. What does it look like when your instructor replies? And you don't have to worry about checking it every 5 minutes. Canvas makes it super obvious. Just look at that inbox icon in the main menu again. See that little blue dot? When that appears, that's Canvas telling you, hey, you've got mail. It's your signal that a reply is waiting for you. So as soon as you see that blue dot, just click on the inbox. The new message thread will be highlighted so you can't miss it. Just click on that and you're in. You can read the reply and get the guidance you need. Simple as that. All right, let's zoom out for a second and talk about why this all matters so much. Because really, mastering the Canvas inbox isn't just about sending and receiving messages. It's about taking ownership of your learning and stepping into your role as a professional. I want you to really hear this. The inbox is your tool. It's how you get answers, how you get clarification, and how you build a professional relationship with your instructors. When you use it effectively, you're not waiting for help. You're actively going out and getting it. You're empowering yourself. And here's the coolest part. Every professional habit you build right now in Project Pace, that clear communication, that respectful tone, those are the exact same skills you're going to be teaching and modeling for your very own students someday soon. So I'll leave you with this question to think about. How can getting really good at this one simple tool today shape the incredible educator you are already on your way to becoming tomorrow?